arbitrary representation of SO d minus 1 or d minus 2, depending on whether the particle is massive or massless. This you remember, right? You get some representations by quantizing the effective Clifford algebra, and then you tensor product it with any representation you choose of SO d minus 1 or d minus 2 times R symmetric. Okay? Now clearly the smallest representations you will get are those in which you take the universal multiplet and tensor it with just identity here. Those were the kinds of examples we worked out yesterday, where we just worked out the universal multiplet, the universal content, and tensor it with nothing. Now, I'm going to ask the following question. What happens to these multiplets as the number of supercharges increases? Okay? So let's, because it's of most physical importance, let's look at the massless case. So suppose the total number of supercharges is n. Now you remember that in the massless case, n by 2 of these supercharges were inactive. Okay? So the effective Clifford algebra is made out of n by 2 charges. Now, of these n by 2 charges, n by 4 of them are creation operators, and n by 4 of them are annihilation operators in the Clifford algebra. And like we did in our examples yesterday, it's always possible to choose one of let's say the creation operators, the n by 4 creation operators, all to have spin half under one of the planes of SOD minus 2. Then the annihilation operators will have spin minus half under that plane. These two will be complex conjugates of each other. That's the convention we used in our examples last class. Okay? So now, let's suppose we choose the creation operators all to have spin half. Okay? If we choose the creation operators all to have spin half, and we have n by 4 of them acting, then the range of spins that we get, the difference between the lowest spin and the highest spin under this SO2 is what? It's n divided by 8. Right? Because each of these n by 4 creation operators increases the spin by half. So you can act with it 0 times, or 1 times, or 2 times, up to n by 4 times. N by 4 into half is the increase in the range of spins. Is this clear? Okay. So we have these n by 4 guys. Right. Now, suppose I have a particle of spin s. Let's say I have a particle of spin 1. Let's say gauge boson. Okay? Let's say my supermultiplet has no particles of spins larger than 1. Suppose that were the case. Then the range of variation of the spin can go from 1 to minus 1. Is this clear? Under any of these planes? So the range of variation, the difference between the maximum spin and the minimum spin is at most 2. Is this clear? And therefore, if we impose the condition that our universal multiplet has no particles of spin larger than 1, then we get the inequality that this has to be less than equal to 2. And so we conclude that n has to be less than equal to 16. Is this clear? Okay. Now, of course, I put the less than equal to because we're really doing it for the universal multiplet. You can get more spins by tensoring it with other stuff, but you can never get less. Okay, when you test, representations get bigger. I mean, one direction they always get bigger. Okay? And so, if we want no more than spins, particles of no more than spin 1, we cannot deal with a theory with more than 16 supercharges. Any such theory will always have massless particles of spin greater than 1. Now, why am I obsessing with massless particles of spin greater than 1? I mean, what's special about 1? What's special about 1 is the following. As far as we know, as far as we've been able to understand, okay, we have not been able to construct interacting quantum field theories with particles, with massless particles of spins larger than 1. Okay. Whether or not this is impossible, one should be careful about saying. Certainly there are no examples. Okay. So if we take that as a guiding principle, the quantum field theories have massless particles in the range of spins -1 to spins 1 or less. Okay? Then we come to the conclusion that you cannot have quantum field theories, okay, with n greater than 16. N is equal to 16. 16 supercharges is the largest number of supersymmetries. Gravity is not a quantum field theory. Okay, yes, gravity is excellent. I mean quantum field theories that we understand as sensible, well-defined quantum field theories. It's worse than renormalized. I mean, so far the counting is completely independent of number of dimensions. This depends on number of supercharges. Is this clear? So QFT is a tentative conclusion because it made some assumptions, but have n less than equal to 16. The maximum number of supersymmetries you can have in a quantum field theory, at least according to my assumptions, is 16. Okay, and we have several examples of quantum field theories with 16 supercharges. The best, most famous example is n equals 4 super Yang-Mills theory, which in the counting of our supersymmetries from yesterday, or last class, has 4, n equals 4 in 4 dimensions. In 4 dimensions, n equals 1 had a while supercharge, which was too complex, so 4. So n equals 4 is 4 into 4, so 16. So that maxes out that counting. Is this clear? Okay. Now, this also gives us a bound on the number of dimensions in which we could possibly have a supersymmetric quantum field. Okay? Just because the number of components in a spinner grows with dimension. Okay? In fact, the largest dimension in which you can have a supersymmetric quantum field theory, according to this count, is d equals 10. Okay? And d equals 10 works because the chiral spinner in 10 dimensions is 16 dimensional. What? 11, no quantum field theory. You can have gravity. Gravity is not a quantum field theory. Okay? You see, the spinner in 11 dimensions is a chiral plus an anti-chiral spinner of the 10 dimensions. That is twice the number of components. In fact, we worked out yesterday in our example, we worked out the multiplet of the Yang-Mills multiplet in d equals 10. And at least just, naively, just from this representation theory, that's a fine representation. You can write down a Lagrangian for the d equals 10 Yang-Mills theory. It appears on the world volume of D9 branes and string theory. There's no issue at this level. Okay? So already from supersymmetry representation theory, we've concluded something sort of interesting. If we're interested in supersymmetric quantum field theories, these theories do not exist, as far as we can tell, below 10 dimensions, do not exist with larger than 16 supersymmetries. These are connected but distinct statements. Okay. Now, the next question is, do supersymmetric quantum field theories exist in all dimensions up to 10? Okay? We've got pretty plausible, it seems plausible that they don't exist above 10 dimensions. Do they exist in dimensions less than 10? Okay, let's see. So in order to try to address this question, what we're going to do is the following. In order to try to address this question, we're going to remind ourselves what quantum field theories are. how are quantum field theories, not just at some crude level of writing down some Lagrangian, but in their guts, what are quantum field theories? Okay. So, in my opinion, the best way of thinking of a quantum field theory is as defined as a renormalization group flow away from something. Now, this thing, whatever it is, could be two things. It could be a free theory, or it could be a non-trivial conformal field theory. Okay? So quantum field theories are defined as renormalization group flows away from either free theories or conformal field theories. Okay? I'm making this distinction because sometimes free theories are not conformal. For instance, a free Yang-Mills theory outside 4 dimensions is not conformal. Okay. Again, as far as we understand, all quantum field theories are defined in this way. They're defined by either a non-trivial UV fixed point or a fixed free theory in the UV, and then a renormalization group flow away from that. Okay, so we have two options for defining quantum field theories. Either we've got a free theory, and we flow away from it, or we've got an interacting non-trivial interacting conformal field theory, and we flow away from it. Yes. A theory is a set of observables, right? Correlation functions. No, there's no semantics. The theory is what allows you to calculate everything. Okay? But that theory is defined at a technical level by an RG flow. And perhaps I haven't understood your question. No. You see, what you have is let's say a conformal field theory deformed by a relevant operator. That deformation generates a flow. Okay, let's talk about it later. Okay, excellent. So now we've got two options for defining non-trivial supersymmetric field theories. Either we look for flows away from free theories, or we look for flows away from interacting conformal field theories. Now, flows from free theories are easy to control. Okay, because what you want is you want to be able to identify a free theory, and then you want to be able to identify a relevant operator around that free theory. But since the theory is free, it's easy to check whether the operators are relevant or not. Okay? And actually, supersymmetry plays very little role in what I'm going to say next. As far as free theories, flows away from free theories do not exist. For d greater than 4. You take all the free theories in the world, you write down the relevant operators that are not just mass terms. Of course, sorry, not free, non-free. Okay, you can always write down mass terms that are relevant operators. But any interacting operator does not exist in d greater than 4. For instance, if you take just a plane and give rise to a stable theory, as far as we understand. For instance, suppose we had a scalar field theory, and we insisted on putting a phi to the 4 coupling to prevent instabilities associated with the phi to the 3 coupling. Okay? Phi to the 4, as you know, is classically marginal in d equals 4, and becomes classically irrelevant above d equals 4. So it doesn't, this operator cannot be added to your Lagrangian to define a flow. Okay? And this is true of every example we know of. Okay, there's some analysis you have to do here, but at least it sounds plausible that this is true. You have to rule out things like phi cube theory, which reasonably can be ruled out. Okay, so this scheme for defining supersymmetric field theories by starting from free theories, which certainly exist, all the way up to d equals 10. There are the supermultiplets exist, the theories seem to exist. This strategy seems to fail for d above 4, and actually this has very little to do with supersymmetry. Defining quantum field theories in d above 4 as flows away from fixed theories has never been successful. Okay? So if supersymmetric theories exist in the window of 4 to 10, okay, above 4, in the window 5, 6, 7, 8 up to 10. Then they have to be defined by a more sophisticated procedure, namely throws away from superconformal fixed points. Yes? No, I've not said anything about non-trivial fixed points. No, what I've said is that a flow away from a free theory by an operator that is not quadratic. Okay, the theory is free, but the operator is not a quadratic operator. So the whole flow is not free. Yes? You cannot find interacting relevant operators, apart from the mass, or d greater than 4, and not violate some other basic property. For instance, phi cube is relevant in d greater than 4, but typically leads to instabilities and problems. Okay, nobody successfully managed to find at least one good example. Okay, all these statements should be taken with pinches of salt because much of it is dependent on, experience. But it sounds reasonable. No example, at least. Okay, so now so let's look then for the other strategy of trying to find define supersymmetric theories as flows away from conformal theories. Now this becomes interesting. This becomes interesting because now we have something new. What we have is the following. See, suppose you've got a supersymmetric theory. It implements the SUSY algebra. And recall that in the supersymmetry algebra, Q was in a spinor of SO d, d minus 1, 1. But if you've got a non-trivial conformal field theory, then the Lorentz algebra is enhanced to SO d, 2. The conformal algebra. This all of you know, right? Yes? 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 No, I don't consider a counterexample because you cannot define it starting from the free theory and flowing away from it. Yes? You see? So the way you want to define a quantum field theory is start in the UV from a free theory and flow away from it. This is how Wilson-Fisher theory is defined. This is how Yang-Mills theory is defined. No, that doesn't make sense, right? We want to control. The problem in defining quantum field theories is to control their UV behavior. Yeah. So of course, there may be some completion of this theory, but that's not a definite. Until we find that completion, we haven't defined the theory. Okay? Excellent. Other questions or comments? Fine. So let's see. So as we were saying, the Lorentz algebra, the Lorentz group, is enhanced to the conformal group in a conformal field theory. Now, this tells you that something interesting is going on. Because you see, supersymmetry is transformed as spinors of the Lorentz group. But the Lorentz group is enhanced to the conformal group. So it cannot be that the end of the story is just that you have supersymmetry and conformal invariance by themselves. Because you see, what would happen if you took an SO d minus 1, 1 spinor is not a representation of SO d minus 2. D, 2. So you need so if a theory is both supersymmetric and conformally invariant, it needs to enjoy invariance under a bigger algebra than either supersymmetry or conformal invariance. Is this clear? So this is the reason I'm talking about this. Yes, I'm looking for UV fixed points that could potentially define supersymmetric quantum field theories. Okay, fine. So now, in particular, we have to complete the supercharges in the theory into supercharges that transform as spinors of SO d, 2. or some representation of SOD comma 2 such that you have the restriction to SOD minus D minus 1 comma 1 is a spinor, the natural guess is a spinor. Okay. So what we need to do is to find a bigger algebra. What we need to do is to find a bigger algebra that includes SOD minus 2 comma 2, sorry, SOD comma 2 as a subalgebra, and has the odd charges transforming spinorially under SOD comma 2. Okay? Now, you know, the really nice thing about SOD comma 2 is it takes the momenta of, one of the really nice things about SOD comma 2 is it takes the generators that were momenta in just the Lorentz group and incorporate them into the analytic continuation of the sign flip of a compact group. You see, the Poincare group was not compact in any sense. You couldn't change a sign. You couldn't do a Wick rotation and make it a compact group because of the R4 translations. Okay, but SOD D comma 2, which incorporates also the momenta as part of its generators, is now a compact group if you just flip a few signs, if you just change it to SO D plus 2. Now that's very nice because mathematicians love compact groups. Okay? And the representation theory of compact groups is very well understood. So what we're looking for, ignoring issues of signs, ignoring issues of eyes, we'll sprinkle eyes in later on to get the right reality properties. You know, mathematicians often don't care about reality properties in doing representation. Okay? So, ignoring issues of the signature, what we're looking for is some supergroup which has SO D plus 2 as a subgroup and has the fermionic generators transforming spinorially under SOD D plus 2. Now, so the first thing we need to do is to find the algebra, just like we did for supersymmetric. Then we can think about other things. Okay? So now we can ask, let's try to find this algebra. Luckily, this is a problem that our mathematician friends have solved. What is the problem they solved? Mathematicians have classified all compact Lie superalgebras. Okay, it's a generalization of the classification of all compact Lie algebras that all of you are familiar with. Okay? And just to show you that I'm not bluffing, I'm going to write down the list of these compact Lie superalgebras. There'll be a bunch of names which will mean nothing to you. But the important point is that I will also write down what the bosonic subgroups of the algebras are and how the fermionic charges transform under these bosonic subgroups. Okay, so the names don't matter. It's just so that you see them once, so that when you see them next, you don't feel scared. So this is okay. I'm going to write the name, the bosonic subgroups. And now, sorry, I'm in the convention that Naveen doesn't like. SPN is used instead of what he would call SP2N. I'm sorry, I'll just stick to this, otherwise I'll make a mistake with my notes. Okay. Okay. So this is the bosonic subgroup, and this is how the fermionic charges transform under it. They transform in the vector times vector. This is a name for the full group. It means very little. I mean, unless you know it already. This is the bosonic subgroup, and this is how the fermionic charges transform under it. Okay. There's DMN, which has SO2M times SPN. Again, the things transform like vector times vector. You understand what I mean by vector of SON, right? And SPN, just the defining representation. Okay. Then there's this strange group called D2, 1, alpha. which has SU2 times SU2 times SU2. And this transforms into 2 cross 2 cross 2, the spinner times spinner times spinner of SU2. Okay. Then we have the group which is called F of G, in which the bosonic subgroup transforms like is SO7 times SU2. And here we get spinner times vector. Okay, then we have G3. Okay, we have G3, which is G2 times SU2, and this is spinner times vector. Vector means, the 2 of SU2. It's just the defining representation, always. That's my notation. Okay, then there is Dn, which has SU2, and this transforms in the adjoint, the 3 of SU2. What is a spinner of G2? It's a representation of G2 that will not bother us in the rest of these lectures. Okay, just so that we get somewhere, it will not. This group will be of no importance to us later. No, they're not. What is this list? This list is the set of all consistent, compact Lie superalgebras. The mathematicians didn't care about whether the fermionic generators were spinners or not. Okay, I'm just giving you the full list, and then we're going to draw a physical conclusion. All I've done here is take a mathematics paper and copy. Take a mathematics paper, translate, and copy. Okay. Then there's AMN, SUM times SUN times U1. And the generators are in vector times vector. Then there's a special case. This is M not equal to N. There's a special case AMM, in which you have SUM times SUM. What am I doing? Sorry. Yeah, right. SUM times SUM. And again, there's vector times vector. And finally, there's a group called CN, which has some stuff. Okay, it's like the spinorial representation. I won't write it down because I have to try to explain it. Something will not be important. Okay. Hey. Now, what we want to do, our goal was to find the superconformal algebra. Our goal was to find the superconformal algebra. So we wanted to find a group that had SOD, 2. Now, we're willing to sprinkle i's all over the place. So SOD, 2 is the same as SOD plus 2. Okay. First sight looks good. There are SOs here and SOs here. Looks good. But there's a problem. And the problem is this stuff. That the supercharges don't transform as spinors under the SOs, they transform as vectors. No good. We won't have supersymmetry as a subalgebra. Okay? So now you might think that you've, yeah. The middle column is the bosonic subgroup of the Lie superalgebra. The fermionic, okay. So let's look at supersymmetry. The supersymmetry algebra, the bosonic subalgebra was just Poincare, was the Poincare group, and the fermionic algebra were the supersymmetries. This does not include the supersymmetry. What I've told you here is in what representation of the bosonic subgroup the supersymmetries transform. So these are the supersymmetries. Is this clear? Is this clear? Excellent. So now what do we have? What we have is the group. We want to look for supergroups in which we've got a factor of SOD plus 2, and we've got supercharges transforming as spinors. Now you look here, scan the list for SOs, and you say, aha, there's an SO7, and aha, there's a spinor. It's a bit strange, since under SU2 there's just one representation, just the two-dimensional representation. But anyway, so you see that there exists a D equals 5 superconformal algebra. And this thing here, this SU2, we would have called it SP1 in our discussion from yesterday. If you go back to your notes from yesterday, you will identify as the R charge, okay, with n equals 1. What? Where did I get D equals 5? Because I equated 5 plus 2 to 7. I equated D plus 2 to 7, because this was SO7. Okay, D equals 5, n equals 1, superconformal algebra. And therefore, you might think you proved a theorem. The only superconformal algebras in the world exist at D equals 5 and have n equals 1, because there's no other SO here. That's quite a theorem. It would tell you that it would be quite a theorem. It's not true. Okay, why is it not true? Why it's not true is that why you don't see SOs in the list. At low ranks, two different names sometimes describe the same algebra. The famous example is SU2 is SO3. So you might somewhere see an SO, something that looks like that doesn't look like an SO, but actually is. So let's look at that case by case. Okay, let's start with D equals 2 and 1. We've heard all about, right? We won't bother about that. Let's start with D equals 3. Okay, in D equals 3, we're looking for SO5. Okay, now what is SO5? Is there another name for SO5? Anyone? SP4, what I call SP2. Okay, that's equal to SP2. Excellent. SO5 is also SP2. And what is the spinorial representation of SO5 in terms of SP2? It's a vector of SP2. It's a four-dimensional representation. Okay. So now look here. Even though we didn't have an SO, we did have an SP. Okay? And we had something transforming in the vector of SP. So we choose this guy to be 2, either here or here. We find that BM2 and DM2 are superconformal algebras in which the supercharge transforms in the spinor of SO5 and then has an R symmetry. Okay? The R symmetry here is either SO2M plus 1 or SO2M. So any SO. Now, if you go back to our list from yesterday, you will see that in 3 dimensions we had n supercharges having R symmetry SON. So that tells you have a superconformal algebra in 3 dimensions for every n, because this could be even or odd. Okay? So D equals 3, check. Superconformal algebra, all in. Okay, so D equals 3 superconformal field theories are possible. That's good. It's good news. What about D equals 4? Are we going to kill N equals 4 Yang-Mills or not? Okay. Let's look for D equals 4. So for D equals 4, what are we looking for? For D equals 4, we're looking for SO6. Does anyone know of an alias for SO6, another name for SO6? SU4. Great. So we're looking for SU4. Okay. Does anyone know the spinor of SO6 transforms in what representation of SU4? Vector. Fantastic. So can you see an SU in this table with a vectorial representation? Of course you can. Right. So if we do A, 4, comma, anything, N, that gives us a superconformal algebra whose R symmetry is either SUN times U1 if N is not equal to 4, or SU4 if N is equal to 4. And if you go back to our SUN times U1, of course, is just UN. Okay, so if you go back to our list of R symmetries for D equals 4, you'll find that N supercharges had R symmetry UN. Okay, it's an interesting fact that the superconformal algebra has all of that R symmetry in every other dimension, in every case other than 4. But in the case of 4, the U1 decouples. It's just true. It's part of their list. How could we argue with that? You can check. All this can be checked by hand. But anyway, let's move on. Okay, so D equals 4, check, all N. So N equals 4, Yang-Mills lives to see another day. Okay, great. D equals 5 we've dealt with. What about D equals 6? We're looking for SO8. Okay? Please. There's only N equals 1. It's interesting, right? The supersymmetry algebra existed for all N. Okay? But the superconformal algebra exists only for N equals 1. Okay, so there does not exist such a thing as an N equals 2 supersymmetric, superconformal 5-dimensional theory. You know that without doing any work. Okay. Though it would have had 16 supercharges, and so would not have been ruled out from our crude consideration. No. Each algebra has its own peculiarity. You see, this dimensional, it's not like that. Had it been like that, it would have been uniform in dimension. Right. You see, physically, you shouldn't expect that, because when you put a circle, you break conformal invariance. You're going to flow to some new thing, if you flow to something at all. So there's no reason it had to be. Right. Because going from 4 to 5 necessarily involves a scale. And 5 to 4 necessarily involves a scale. Okay, excellent. Now, what about 8? Who knows another name for SO8? What? SO8. That's an excellent answer. SO8 is another name for SO8. You might think I'm being stupid here, but it's not being stupid. See, SO8 has this wonderful property of triality. Do you know this property? This is an automorphism. It's a way in which, let me say it simply. SO8 has 3 8-dimensional representations. The chiral spinor, the antichiral spinor, and the vector. And the properties of these representations are all identical. So it's a matter of choice whether you call a representation a chiral spinor, a spinor, or a vector. You can always redefine the generators of SO8 so that what is a chiral spinor with one choice of generators is a vector with another linear combination of these generators. Okay, do you know this wonderful property? It's a fantastic thing. You should learn about it. I won't tell you much more. But it's a fantastic thing. It's a beautiful. SO8 is a very special group in many ways. Okay? So, that helps us out. Because, you see here, if we wanted SO8, we had only the vector representation. But the vector representation is not invariantly distinct from the spinor representation. So it's actually we do have an algebra with the spinor representation. Now, which spinor representation? Well, by triality, you can make it either chiral or antichiral. But you can't do both. Right? You can make a triality move once, and your representation becomes a chiral spinor. You can make it twice, it becomes an antichiral spinor. But there's no way you can generate both chiral and antichiral spinors. Now, if you go back to our list of supersymmetries, you will see that in D equals 6, our supersymmetries were labeled by n plus and n minus. They were pseudo-real, so the R-symmetry groups were SPn plus times SPn minus. Half n plus, whatever. Yes? Okay. You've made one choice of basis for the SO8 generators. There is a linear combination. There is a linear transform you can do, such that your new generators have exactly the same commutations relations as the old generators. Okay? But if you do that linear transformation, what was a vector representation for your old generators will be a spinor representation for your new generators. Okay? So which one is correct is up to you, because there's no way of distinguishing which choice is better. Okay? Questions, comments? No, it doesn't mean it's SP4. Why do you say that? I didn't understand that. But it just means that SO8 has this property of being able to, that the spinor representation in every way behaves identical to the vector representation. The spin group of SO8. You're talking about global features?
Yeah.
I refuse to answer questions about global features. Okay, forget it. It's not relevant, right? There are 3 different representations. Every observer will agree there are 3 different representations. One observer will say this one's vector, this one's chiral spinor, this one's antichiral spinor. Another guy will say this one's vector, this one's, everyone will agree that there are chiral spinors and antichiral spinors and vectors, but they won't agree on the labels for them. Okay? Observers means different choices of, yeah. Okay, is this clear? So, even though it looks like our supercharges were in the vector representation here, by redefinition, they become the spinor representation. And then the R symmetry is SPn for any n. So D equals 6, check. We have superconformal algebras of the form n, 0 or 0, n. N plus could be anything, n minus could be anything, but there's no such thing as a superconformal algebra with 1, 1. That's sort of interesting again, because of course there are field theories with 1, 1. At least that supersymmetry algebra exists with 1, 1. Okay, it has as much supersymmetry as 2, 0. 16 supercharges. Our criterion would not have disallowed it. But the superconformal algebra does not exist. So the theory does not make sense. Okay? What? Yes. Yes. You see, suppose I looked at the D equals 6, 1, 1 algebra. Supersymmetry algebra. That exists. Makes perfect sense. Okay? But you could ask, can you enhance this to the superconformal algebra? The answer is no. There does not exist an algebra. You would not have seen this, the number of supersymmetries, if you do the counting, in 1, 1, same as number of supersymmetries in 2, 0. Just total number of supercharges, which is 16, which is allowed by that crude criterion. So it's not obvious that there did not exist 1, 1 superconformal field theories, but it's true. Because of our mathematician friends. Exactly. That's the statement. Because all the representations here, the representations were one representation. Under triality, that doesn't change. You can change the label, but you can't change the fact that they were all in the same representation. Is this clear? Yes. So the algebra is D for n. Exactly. Okay. 1, 1. Any n, n prime where one of the two n's is non-zero is ruled out. Okay, the only things that exist are n comma 0. Okay, what about d equals 7? What about 9 dimensions? Okay. Oh, what can we say about supersymmetry algebras? Who knows another name for SO9? Nobody. That's very good, because as far as I know, it doesn't exist. Who knows of a magical property like triality for SO9? Nobody, because it doesn't exist. And so on. We could go through the list, 10, 11, up to infinity. None of them work. Okay. There exist no superconformal algebras in d greater than 6. And therefore, if we define supersymmetric quantum field theories as flows away from non-trivial fixed points of the superconformal, non-trivial fixed points of the renormalization group, supersymmetric field theories do not exist in larger than 6 dimensions. Yes? Flowing from the fixed point. I'm not going to a fixed point, I'm flowing from a fixed point. I'm trying to define the theory. There's another separate question you can ask about trying to unearth interesting critical behavior at low energies. That's an interesting question. That's not the question of interest to me at the moment. The question I'm trying to ask is, how can we define quantum field theories in higher than 6 dimensions? Quantum field theories in higher than in any dimension is defined as flows away from fixed points. Okay? You have no leeway. The fixed point doesn't exist, there's nothing to flow away from. Of the fixed points, but I will say again, how are quantum field theories defined? Quantum field theories are defined as flows away from fixed points, either free or non-trivial. No, not yet. We can get information. If we had 10 more lectures, I would have given you lots more information. Yeah. Now, we do not know of any sensible, for instance, the superconformal algebra in 4 dimensions exists for all n. But for the reasons that related to the reasons I mentioned there, we do not know of any sensible quantum field theory for n greater than 4. So, putting together all these criteria, that n less than equal to 16, and the list I've told you about, I think there are examples of every group. If you include that n less than equal to 16 and this. Okay? Fine. Now, the rest of the lecture I wanted to talk about, okay, we have half an hour, so I wanted to at least briefly tell you about Seiberg duality and that kind of stuff. But I'll just end this part with one comment. Okay, the self-contained part of these lectures, as you will see, were about symmetry. Okay? I would have loved to tell you about the representation theory of the superconformal algebra, but we don't have the time. Which disconnected short multiplets? In the superconformal algebra, Indranil, I have to tell you later. You know, because I would have to tell everyone what disconnected means, what short multiplets mean. You know, there's not time for it. Listen, yes. No, so now that's an interesting question. The question was, what is the connection between these restrictions and those groups? And they're logically distinct. As we have seen, here you have superconformal algebras for all n. And that will give you spins much larger than 1. Okay? This is just a question about the existence of an algebra. There's a separate question about the existence of physically sensible representations. That's a completely separate question which we'll have to discuss separately. This is a cruder question, also more sophisticated. It's cruder because it's only about algebra, more sophisticated because it inputs the information of conformal symmetry. Yes? Okay, this non-free is badly written. Free theories with non-free relevant deformations that do not cause an instability. Okay? Because, what? Because in D equals 6 there's a CFT, but that CFT is not defined by the flow away from a free theory. You know, roughly when I was growing up as a physicist in the early 90s, the lore was that quantum field theories do not exist in greater than 4 dimensions. Because the only way people knew how to define quantum field theories at that point was to take a free theory, define a flow away from the free theory, and go to something interesting. That's what Wilson Fisher did. How successful they were. They won a Nobel Prize. Okay, that was the lore. And for this reason, the expectation was that quantum field theories do not. Of course, it was never very good lore, because there was always the possibility that quantum field theories would exist, defined in the UV by non-trivial fixed points of the renormalization group. Okay? But you know, we're limited by what we can do. In non-supersymmetric field theories, if such fixed points of the renormalization group existed, and we could access them by flowing away from something which we could control. And what can we control? What is roughly the state of technology of human beings? Roughly, it's free theories. Okay? So what could we, if we couldn't approach them by flowing away from free theories, how would we ever know they existed? Things like that changed dramatically in the 90s because of supersymmetry. Supersymmetry has given us calculational tools, some of which I'll now briefly try to outline for you, which allows us to say exact things about things that are not just flows away from free theories. Actually, the thing I'm going to talk about is a flow from free theories. But the same techniques can be used for more interesting things. Okay, so the 6-dimensional theory exists, and we know it exists from various considerations that are not flows from free theories. It's the IR of something, which is not a free theory, not a free quantum field theory. Okay, and the only real reason we know all this happens is because of supersymmetry. Without supersymmetry, we wouldn't have been able to control anything. Okay, so supersymmetry has greatly enlarged our scope in the study of quantum field theory. It's allowed us to do things that we could not do before, namely look at theories that are non-trivial fixed points of the renormalization group that do not exist as endpoints of flows away from free theories. Any superconformal fixed point in 5 or 6 dimensions is not the endpoint of a flow from a free theory, because no such thing exists as far as we know. Okay? Yet we can understand it, we can study it, because of some exact control. So, the last comment I wanted to make before we proceed, I want to give you a flavor of how you can control things exactly. Okay? The last, yes. That's an excellent question. That was the last comment I was going to make. Do there exist CFTs above 6 dimensions? And the answer is nobody knows. How would we know? The only way we could know is to somehow prove a theorem that they don't exist, or find an example that they do. We do not have the technology to find an example that they do, because for non-supersymmetric theories, perhaps you would have got lucky with large N, but it doesn't work. Okay. For non-supersymmetric theories, apart from large N, the only technology we have is flowing away from fixed free theories. That doesn't work. There could be zillions of them out there. We wouldn't know. Okay? The algebra exists because the conformal algebra exists in all dimensions. You could try Bootstrap. I agree. So you could try Bootstrap. So that's another interesting idea. You could try Bootstrap. And the most convincing thing from Bootstrap would be a theorem that no solution exists. Because if a solution exists from the Bootstrap, you might still wonder if it's a conformal field theory. For instance, in 2 dimensions, if you take a good conformal field theory, and you overfold it, and throw away the twisted sectors, that will satisfy all the constraints of the Bootstrap, but it's not a good conformal field theory. Okay? So this conformal Bootstrap is necessary, not sufficient, should be taken with a pinch of salt, so on. But you might be able to use the Bootstrap to prove the negative result, that no theories exist above 6 dimensions. Then it would be true. Because if a theory exists, it must satisfy the Bootstrap. Yes? Louder. Because it won't be modular element. Yes. And that, of course, leads to all kinds of other problems as well. But yeah, any attempt to define it on higher genus surfaces. Right. Exactly. Okay. Other questions or comments? Excellent. So it's a fantastic problem of theoretical physics to classify all fixed points of the renormalization group. Maybe I should call it a fantastic problem of theoretical mathematics. I'm not sure which one. Okay. This is a much more plausible program with supersymmetric theories. First, because we know the end of the dimension. Second, because everything's under better control. Okay. But the really interesting question is to do it for all quantum field theories. Perhaps using the Bootstrap, perhaps using some other more novel idea. If this program can be achieved, it would be enormous progress in theoretical physics. It's a fantastic problem, one that sounds very hard. But part of solving this problem would be answering Naveen's question. Is there a highest dimension in which fixed points of the renormalization group exist or not? Look at the state of our ignorance, such an elementary question. Do field theories exist in a million dimensions? We have no clue. Frankly, we have no clue. You may have your biases, but there's no rationale for that bias. Okay, let's move on. So in the last half an hour of this course, I want to give you a flavor for how supersymmetry can be used to control dynamics. We got a little bit of this flavor in the first lecture when we looked at quantum mechanics. But that was a very crude example for many reasons. A, it was quantum mechanics, but more importantly, B, it had only 2 supercharges. And the real power of supersymmetry starts with 4 or higher supercharges. Okay? So the example that I'm going to tell you about. Okay, so I haven't emphasized enough in these lectures. But the really interesting, you might ask, why should one study supersymmetric quantum field theories at all? Because people have many motivations, some of which are phenomenological. But let us say that from the point of view of theoretical physics, a theorist who looks at phenomenology from a distance, okay? Why would you be interested? What are the structural reasons to study supersymmetric quantum field theories? The reasons are that supersymmetry constrains the theories enough to make several exact calculations possible, while leaving the theories free enough to display extremely rich dynamical behavior. Both these are necessary for the theory to be interesting and for you to be able to say something useful about it. Okay? And I want to give you a very brief flavor of this in the next half an hour. So we're going to study a model. This is a model considered by many people, but studied and cracked by Seiberg in a fantastic set of papers in the mid-1990s. Okay, which somehow revolutionized our study of supersymmetric field, our understanding of the importance of supersymmetry. Okay, and in some sense, the reason we're having lectures like this, even though is because of that work and its follow-ups. So the model we're going to study is supersymmetric gauge theories. In D equals 4, with n is equal to 1. Now, the supersymmetric gauge theory, because it's a gauge theory, it has a gauge boson, and then its multiplet, which you could figure out by the techniques we've learned about in the last few classes, but I won't try to do that for you, is completed with a fermion called the gluino. Okay? So, we've got a chiral fermion and a gauge multiplet, both of which are in the adjoint of the gauge group. Okay? This is the content of what's called the vector multiplet of 4-dimensional supersymmetry. Now, apart from the vector multiplet, you can have other kinds of multiplets of 4-dimensional supersymmetry, one of which we did look at last class, the chiral multiplet. And the content of chiral multiplet is a scalar phi, and it's associated with what's sometimes called chiralino psi. Complex scalar, Weil fermion. Let's look at degree of freedom counting. A gauge boson has 2 bosonic degrees of freedom. A chiral fermion has 2 bosonic degrees of freedom. Why 2? Well, 2 because it's 2-component, because it's complex, and because one component of a fermion counts as half of a boson, because it's the first order equation. So that's 2 into 2 divided by 2, so that's 2. Okay? The number of degrees of freedom of a wild fermion in 4 dimensions, same as that of a gate boson, same as that of a complex scalar. This forms a multiplet, this forms a multiplet. This multiplet will be in the background of everything we're talking about, but we will not explicitly talk about it in these lectures, for reasons you will see. However, these chiral multiplets have to interact with the gauge group. So they have to be in some representation of the gauge group. Okay? We will study the theory with NF quarks. Quarks in the fundamental. So I is equal to 1 to NF. Okay? And NF quarks in the anti-fundamental. Each of these, I call them quarks. What they are chiral multiplets in the fundamental representation of the gauge group. Okay. Now, in a theory with ordinary Yang-Mills theory and gauge bosons, if I told you that I have some number of fermions, so ordinary Yang-Mills theory and fermions, if I told you I have some number of fermions, some representation of the gauge group, what is the Lagrangian? You write it down uniquely, right? There's no ambiguity. Okay? In a similar way, because anything you can write, you can just do minimal coupling of the fermion. You could try to write a psi to the 4 coupling, but that would not be renormalizable. That would not, it would be an irrelevant operator away from some effective free fixed point in the UV. Yes, my Q's are going to be, Q's are in the fundamental, and Q tildes in the anti-fundamental. In a similar way in this theory, okay, apart from possible mass terms for the chiral multiplets, which you could have also put for the fermions, okay, apart from possible mass terms for the chiral multiplets, which to start with we'll set to 0, the Lagrangian of the theory is completely determined just by telling you this gauge, the field content, demanding that the Lagrangian is renormalizable. Okay? And this field content, very much like ordinary fermions with gauge bosons. Okay? For instance, now since we're all experts on chiral multiplets and superpotentials, one of you might have challenged me. One of you might have said, what about writing d2 theta d4x times w of q and q tilde? Suppose I try to add such a term to the Lagrangian. Well, what could it be? You see, anything you add to the Lagrangian, firstly, let's look at this. This quantity here has dimension 4 because of the x, and minus 4 because of the d4x, but dimension minus 3 once you take into account d2 theta. And it's minus 3 because although theta has dimension half, d theta has dimension minus half. Because d theta for a fermionic coordinate, unlike for a bosonic coordinate, is not really an integral, it's a derivative. So it removes the theta. Okay? So this whole thing here is of length dimension 3. Okay? So renormalizable operators are operators with dimension 3 or less. I mean, renormalizable superpotentials have dimension 3 or less. Okay? So what can you put in here which is dimension 3 or less? Well, you might think, well, I could put q tilde. That's good. What about q squared q tilde? That looks like dimension 3. Q has the same dimension as phi, which is 1 in 4 dimensions. The problem with this is that whatever you put in your Lagrangian has to be gauge invariant. Q has a fundamental index that can contract with the anti-fundamental index of the q tilde. Okay? But you can't have a dangling q left around. The next thing you could do is q tilde to the power 4, which is 1 dimension above renormalizable. It doesn't work. So the renormalizable actions, the only thing you can add, only freedom you have in superpotential addition is a mass term. QQ tilde is a mass term. I haven't even explained that very properly to you. But supersymmetry with this content and renormalizable fixes the Lagrangian completely up to mass terms. Okay, so if you set mass terms to 0, it fixes it completely. Louder, louder. QQ tilde to the power 4, QQ tilde square, so Q, roughly Q to the power 4, has dimension 4, but renormalizable operators have dimension 3 or less because of the d2 theta. Now you might say, what, this is all bullshit. I mean, I know you take your supersymmetry away, I know renormalizable operators are okay if they're 4. Be careful. Do you remember in the last class we showed that F, that there was a term in this, when you expand the d2 theta, that was F times W prime. From the kinetic term of the scalars, just like in the Yang-Mills theory, just like in the quantum mechanics that we studied in the first lecture, there's a term like F square. So you complete this, like you eliminate the auxiliary multiplet, the actual potential in your theory is W prime squared. That's why if W had Q to the 4, W prime would have Q cube, W prime square would have Q to the 6, which you know is non-renormalizable. Okay? Dimension counting is a cheap way to say this. Is this clear? Okay, great. So now, we've got a well-posed problem. Moreover, I mean, if we've got a well-posed problem that at least dimensionally is well-posed. Yes? If it was SU3, you could put 3 quarks. That's true. That's true. That would be a special case. I agree. And that's something you would have to discuss separately. I'm not in that special case. Good point. Okay. Yeah, that's interesting and probably has been studied. Yeah. But let's stay away from that special case. Okay. So now this naively gives us a well-posed problem. However, is the problem really well-posed? Because the supersymmetric theory, like ordinary Yang-Mills theory, has a classically dimensional operator, dimensionless operator, namely the coupling constant. When something's classically dimensionless, quantum effects can make it go either way. This is the question of what the beta function of the theory is. Okay? So what is the one-loop beta function of this theory? What is the one-loop beta function of this theory? Okay? Turns out that the answer, it's not hard to do the calculation. Turns out that the answer is the following. The one-loop beta function is the one that makes that ensures asymptotic freedom for NF less than 3NC. And the other behavior, the behavior of flowing to a weak theory, a weak coupling in the IR from strong coupling in the UV. So basically, irrelevant behavior for NF greater than NC. Okay? So, if we want to use our first strategy to define this quantum field theory, namely as a flow away from the IR, a flow away from a free theory, we need the theory to be asymptotically free. In the other case, maybe the theory is well defined, but we need a definition. Okay? So this theory is well defined for NF less than 3NC. Okay, so it's a genuinely well-posed question. I've got this Lagrangian. I want to know, the question I'm going to ask is what is the dynamics of this theory in the infrared? Okay, it's a similar question to the question we ask in QCD. What is the dynamics of the theory of QCD in the infrared? And just to remind you, this is far from a trivial question. Because if you gave your beginning graduate student the QCD Lagrangian and ask him what is the dynamics of QCD in the infrared, he will say it's the dynamics of scattering gluons. And that's nonsense. QCD has a mass gap, there are no gluons. The particles are glue balls. It's not at all visible from the Lagrangian. I'm talking about pure Yang-Mills, even more interesting with quarks. Okay, so clearly this is a very interesting question as long as supersymmetry preserves at least some of the dynamical richness of real QCD? So it's a great question to ask. Can we answer it? Okay. Now, in order to start answering this question, is the problem well posed? Is the question clear? Okay. I'm not sure how much time we'll have for the answer. Well, that's another matter. Okay. Yeah. Okay. In order to start answering this question, we're first going to do something that we've learned over the last 15, 20 years is totally crucial. That is, carefully analyze the symmetries of the problem first. Okay. So the first question we're going to ask is, what are the various symmetries of this theory? First question I'm going to ask, first, before doing anything, I'm going to go back to my algebras, the algebras we so painstakingly created. We have an n equals 1 theory. What was the R symmetry of that algebra? Anyone remember? It was U1. Okay? So we have an n equals 1 theory. The R symmetry of that problem was U1. So one question I'm going to ask is, does there exist an R symmetry? Okay. Next question I'm going to ask is, you see, because the theory is not superconformal, it doesn't have to exist. That's something I should have emphasized more. In the superconformal algebra, the R symmetry is part of the algebra, so it has to exist. Supersymmetric algebra, it was an option. Does there exist an R symmetry in this problem? And what other symmetries exist? Well, yeah. There's no such thing as a real supercharge in 4 dimensions. So n equals 1 means one complex supercharge. Excellent. Great. So what other symmetries exist? Well, you know, we haven't had the time for me to properly explain how to write down kinetic terms in 4 dimensions. Oh, but we did it yesterday. Sorry, the Kähler potential. So apart from the interaction with the gauge field, the kinetic terms were Q of the theory were QI dagger. Sum over I, and a similar term, QI tilde dagger. And this includes some interaction with the gauge field that I'm not going to tell you about. There's some way of doing that. We haven't had the time to discuss that kind of thing well. Okay? The important point, though, is that wherever the interaction with the gauge field is, it goes in here. And so this theory manifestly has a UN times UN flavor symmetry. Is this clear? You just rotate the QIs by a UN matrix and rotate the QI tildes by a different UN matrix. UNF times UNF flavor symmetry. Because the U1s are going to play a special role, we'll write this in a slightly more complicated manner. There's UNF times SUNF times SUNF times U1 times U1 times U1R if it exists. No mass terms. Sorry. I should have said that at the beginning. To start with, we'll switch off all mass terms. Okay? Mass terms will break the symmetry. Okay? So that's why we want to switch off the mass terms. We want to look at maximum symmetry. Okay. Now, I'm going to ask about this R symmetry. Okay, first, we'll do the R symmetry last. Let me, under this symmetry, let me write down the charges of Q and Q tilde. Okay, so let me write it down properly. There's Q tilde, there's SUNF times SUNF times U1, this U1, times U1, that's this U1. Oh no, maybe I'll make linear combinations of these. So you'll see from the charges. Times U1R. Okay. Now, I'll choose so this guy is in the NF of this and in the 0 of this. This guy, of course, is 0 meaning 1. This guy is in the 1 of this and the NF of this. That's obvious, right? Okay. What about these U1s? I'm going to choose linear combinations of these charges so that one of the U1s would be what would have been there. What would have been there had we just had the gauge group in UN rather than SUN. The UN factor of the gauge group had it existed. Under that UN factor, this guy, let's say this guy is charge 1, then this guy is charge -1 because it's anti-fundamental. Okay? So this guy I'll call charge 1 -1. This we'll call U1 baryonic. One means singlet. Is that what the question? Yes, means does not transform. Okay? The other one that I'm going to look at is this U1, the U1 axial. Okay, that's the other linear combination, 1 and 1. Okay. Now, there's this business about the R symmetry, which I'm postponing till we have the following discussion. You see, so far what I've written down is, are symmetries. So far what I've written down are symmetries of the classical problem. But classical symmetries are sometimes anomalous. It's just, there are two U1s, I choose two linear combinations. Okay, this, I give the name under which both have charge 1 axial symmetry, the name under which both have one is charge 1, the other one is charge -1, a baryonic symmetry. The reason I make this linear combinations is that one of them is manifestly non-anomalous. The baryon one is manifestly non-anomalous. Okay, now let's check that immediately. If we look at the anomaly of a U1, and a genuine anomaly, I mean, maybe I should say a non-genuine, I mean, not a Toft anomaly, an anomaly because of the instantons of the gauge group. Okay? You can ask, suppose I've got a U1 current and I want to check whether it's anomalous under the gauge group. Okay? So I'm computing del mu J mu of that U1 current is equal to some number times F wedge F. Let's normalize this F wedge F, whatever the normalization is, 1 by 32 pi square, whatever it is, so that it integrates to an integer. Okay, that's implicit in my definition. I can ask, what is this number? Okay, this of course you can look up Weinberg's book for. Okay, this number comes about because of chiral fermions, and the rule is that you get a factor of 1 times q. So suppose we've got a chiral fermion zeta, which has charge q under the U1 that you're interested in, and is charged in some representation of the gauge group. Okay, the representations of interest to us are the fundamental and the adjoint. Okay, so the rule is that you get a charge q fundamental times 1. So every chiral fermion that's in the fundamental contributes just its charge. Okay? And plus q adjoint times 2nc. To F wedge F. Okay, I'm not going to try to derive this. It comes from some C2R or something or the other, doesn't matter. Right, this is the rule. Okay. So, suppose we've got a current, okay, that has all representations that are charged in it with equal and opposite baryon charge, or equal and opposite U1 charge. Then clearly this thing will cancel. In particular, U1 baryon cancels. Okay, I should have said fundamentals and anti-fundamentals contribute the same way. 5 minutes. Okay. I should have said fundamentals and anti-fundamentals contribute the same. Maybe I should stop. Maybe I should just give you a result. I don't know what to do. Just a minute. But of course, a U1 charge, you can take linear combinations of. No, because U1 commutes with SUNF. you see, UN is at the level of the algebra, SUN times UN. No connection. Okay. Okay. Hey. Okay. I just want, let me write down the Affleck-Dine-Seiberg superpotential. 5, maybe 10 minutes longer. Is that okay? Yeah. Okay. At least that. Yeah. Okay. Now, you see, so this guy is certainly non-anomalous. What about the axial current? The axial current will get a factor of 2NF. The axial current will get a factor of 2NF. So that is anomalous. And the degree of anomaly is 2NF. So the axial symmetry, axial U1 symmetry will be broken down to Z2NF. Okay. Now, but the really interesting thing is this R current. I won't have the time to explain to you. But if you look at the Lagrangian, there also is an R current, an R symmetry, classically. The R symmetry, by definition, is a symmetry under which theta transforms. Another way of saying it is, by definition, is a symmetry under which the gaugino, what did we call it? Chi. It has 0, 0, 0, 0, but it's an R charge 1. Okay, field strength is uncharged, gaugino has charge. Okay, now let us, given an R symmetry, that's the definition. The gaugino has R charge 1, but you know, whether matter multiplets transform or not, that's up to us. Sometimes if you have a superpotential, that forces a particular transformation of matter multiplets. In our case, we have no superpotential, so we are allowed to assign the matter multiplets any charge we like. I'm going to assign the matter multiplets some unknown charge. Let's call it AA. I'll keep them equal for a reason you'll see. Okay? And choose A to make the R symmetry non-anomalous. Okay. Now, I should be clear. A is the charge of the supermultiplet phi. Therefore, the fermion in that supermultiplet has charge A minus 1. The fermion in that supermultiplet has charge A minus 1. It goes, why? Because the supermultiplet is phi plus theta psi. In the gauge multiplet, it's lambda plus theta f. So this is minus 1 when that guy was plus 1. Okay? I'm sorry if you're not really understanding this, but okay. So though the supermultiplet has charge A, the fermions, we'll say secretly, the fermions have charge A minus 1. Now, what is this coefficient of the anomaly for these guys? Well, that's 2NF into A minus 1. Okay? Plus 2NC into 1. Now I'm going to choose A so that this is 0. So A minus 1 is equal to minus 2NC by 2NF, so it's NC by NF. So A is equal to 1, so NF minus NC over NF. Trust I got that right. What 2NC is for the gaugino? Yes. No. This plus this is equal to 0. Okay, I got it right? I didn't mess up a minus sign. Okay. What? Why are what equal? Why are they equal? You see, we could have mixed with a part of the baryon number, but that would not have contributed to the anomaly. The reason we're giving these guys charge is to cancel the anomaly. So there's no reason to give that part. Okay? Therefore, we can replace these A's with NF minus NC by NF and NF minus NC by NF. Okay? Once we do that, the R symmetry is non-anomalous. Okay? Now, we can ask the following question. In the IR, we started with a theory for which the superpotential for the quarks was 0. can it be that dynamical effects generate a superpotential for quarks in the IR? This is a question we're going to ask. This needed some background, but I won't have the time for it. So I'll just answer this question. Okay, the question we're going to ask. Well, if this was the case, then the superpotential generated would have to satisfy some constraints. A, it would have to be holomorphic, because it makes no sense for a superpotential not to be holomorphic. B, it will have to be invariant under all non-anomalous symmetries. Okay? So let's see the non-anomalous, and see it, of course, has to be gauge invariant. Okay. So firstly, let's define the following matrix. Let Mij be equal to Qi, where gauge indices are understood to be contracted. What? I put the J up, you want? Util. Yeah. Okay, you understand this object? That's contraction of gauge indices. This is sometimes called the meson supermultiplet. Okay? Now this thing is gauge invariant, so everything has to be a function of it. Okay, for NF, let's say, everything has to be a function of it. Okay, now, this object under the first SU2, first SUNF transforms like SUNF from the left. Under the second SUNF transforms like SUNF from the right. Remember, these two SUNFs are independent SUNFs. Can you think, how can it be, how can you write down any function of a matrix that will be invariant under independent rotations from left and right? If there was the same rotation, you would do trace to some power. But if it's independent rotations, what do you do? Any suggestions? What? Diagonals? No, not even diagonals. Only similarity transforms preserve the diagonals, not these rotations. There's one natural object, it's the determinant. The determinant of a matrix, we multiply by another matrix. It's a product of determinants. And SUN elements have determinant 1. So the only thing that you can do is to make this a function of determinant of M. Once we've done that, by the way, this U1 baryon is now obvious because we multiply the Q with the Q tilde, so that's invariant. We've taken care of this guy, and this guy. What's left? This guy was there, but it was anomalous, so we won't consider it. Let's look at this guy. Yes? What?
It not be that the dynamics broke the flavor symmetry to some...
It could be. We're assuming that well, you know, let's say this. Dynamics might break it, but it should break it by choosing a vacuum which will break that symmetry. The superpotential should break it. Right? And it will sometimes happen that the dynamics will break it, as we would have seen. Okay, but great. Now, if we take this object now, it has to be invariant under this non-anomalous symmetry. What does invariant mean? You see, thetas transform like, is it 1 or -1 now? -1, I think. -1? -1. One. Right. I think it's 1. At least by my convention. I hope I'm not messing up these conventions. What? Superpotential should have exactly. D thetas, right. have -1 because they're derivatives, and so superpotential should have 2. So the superpotential, because like Loga said, the superpotential here has d2 thetas, which is taking away 2 thetas. Okay, each theta has charge. Has charge. What is it? +1. So then I want -1. Oh God.
+1 d theta is -1.
D theta is, thank you, is -1, and so we need +2. Okay, thank you. So we need some function of this object that has charge +2 under this non-anomalous R symmetry. But you see, we know the charges of Q and Q tilde. The charges just add. Determinant has 2NF times that. Okay, so the R charge of Q of M is equal to 2 times NF minus NC. Of determinative. Because just 2NF times this object here. No. Q has charge Q has charge NF minus NC by NF. Q tilde has the same charge. So M, each matrix element has charge 2 times this. And then it's an NF cross NF matrix, so the determinant has an extra factor of NF. So 2NF times this. That's why the NF cancels in the denominator. Okay? So now, if I want some function that adds up to charge 2, what do I have to do? I have to take determinant of M to the power A such that A times 2 NF minus NC is equal to 2. 2 cancels. So we get A is equal to 1 over NC minus NF. Sorry, A is 1 over NF minus NC, or I'll write it as minus 1 over NC minus NF. Which is the form I want to put it in. And so we get that the dynamics of our theory has a superpotential which of the form determinant of M to the power NC minus NF. 1 over. D to theta. Now this makes up all charges, but it's dimensionally wrong. Okay? If there was a dimensional scale in the problem, and we put the power 3NC minus NF over NC minus NF, then the dimensions will work out right. You can check that. Now, is there a dimensional scale of the problem? We don't quite know, but let's make a guess. Let's suppose that this theory, at least for suitable values of NF, behaves like QCD. So the theory confines in the IR. There is a lambda QCD scale. Okay? Then there is a scale of the problem, lambda QCD. That could be the scale that we could use here. So assuming the theory confines, there's a lambda QCD scale, this could be the superpotential, okay, at least for some values of NF. Now let's see. Okay? And up to a number which we have not yet determined, this is the only possibility for the superpotential. Can you see the power of this? If there is a superpotential, we've uniquely determined it by doing nothing. Can you see the power of it? Where did the power come from? Holomorphicity. Okay. Now, let's see the range of NC and NF for which this is correct. For NC equals NF, things are pretty singular, right? So this is not well defined. No superpotentials around for NC equals NF. What NC greater than NF is okay. What about NF greater than NC? This is not okay. Can anyone tell me why? What? Okay, so what? Oh, okay, but that's a better reason. No, that's 3NC. For NF greater than 3NC, it's not asymptotically big. But what about between NC and 3NC? There's a simpler reason. It's an algebraic reason. Algebraic reason is that M is not just any old matrix. It's a matrix formed by taking dot products of NF vectors. Of vectors which are NC columns. Any such matrix has rank at most NC. So if NF is greater than NC, the determinant of any such matrix vanishes. Okay, so this thing here is nonsense for NF greater than NC. So it makes no sense for NF equals NC, it makes no sense for NF greater than NC. So we've concluded that we've proved a non-renormalization theorem. In this theory, for NF greater than NC, the superpotential is what it was in the bare theory, namely 0. For NF less than equal to NC, sorry, not equal to, less than NC, there's potentially such a superpotential. Actually, it exists. And there's a interesting story about it, but I think I'm going to have to stop now. I'll say 2 more things and so forth. Okay. Let me just tell you the answer, okay. Proceeding along these lines. Actually, this is the most complicated dynamical calculation we're doing. Everything else is basically logic. Adding masses, Higgsing is a beautiful story with no calculation. It's what makes it so beautiful. It's like pure reason. Okay, but I'm just going to give you the answer for what the behavior in the IR is, just to give you a sense of how rich it is. And I'm sorry we didn't have the time to discuss it. I would have loved to, but you can read about it yourself. NF less than NC. All these are conjectures, but very well supported conjectures. NF less than NC, theory confines, and the massless theory has no vacuum. So it's a bit moot to say that it confines. Okay, the massless theory has no vacuum because this superpotential generates a potential that drives the scalar off to infinity. You write down what the potential it is, just drives it off to infinity. However, if you add masses give you a rising potential. So it can stabilize it. And if you add the generic mass, the theory has stable vacuum. Okay? As you take the mass to infinity, the vacuum expectation value of the vacuum of the scale and the vacuum goes to infinity. Okay. NF equals NC. I haven't even had the chance to tell you this, but the classical theory has a moduli space of vacua. I haven't had the chance to tell you about this. I'm sorry about this. You just take it from me. The classical theory has a moduli space of vacua that is where 2NF dimensional. At least when NF is less than N. Yeah, okay. Something near 2NF dimensional. Okay. And this classical moduli space is not lifted. The way a moduli space is lifted is by a superpotential. There's no superpotential, so the classical moduli space is not lifted. However, the classical moduli space, when you look at its topology, has a singular point. The singular point is where the quarks have 0 expectation value and where the gluons classically become massless. You see, I haven't had the time to, so much of physics I haven't had the time to tell you about, but on the moduli space, the gauge group is Higgsed. So the gauge bosons are massive, so we need only to talk about the scalars, the chiral multiplets. But if you get to a place where the Higgsing goes away, you've got new massless degrees of freedom, and you need to talk about the gauge bosons. If you don't talk about that, you just talk about the chiral multiplets, you'd see singular dynamics. In the quantum theory, this singularity is smoothened out. Okay? This is the sign of confinement. The place where massless gluons would have given you a singularity no longer exists. Okay? It's a beautiful story which is some quite clear demonstration of confinement. And you know, the point where the classical theory would have been singular is the point where all symmetries of the problem would have been restored. In this smoothing out, it turns out that there's no point where all symmetries of the problem are restored. So at least some global symmetry is always broken, like Sujay asked. And so this is what Seiberg calls confinement with chiral symmetry breaking. With some abuse of language, he calls these symmetries chiral symmetry. What? All of these symmetries. The set of symmetries together are called, it's confinement with breaking of some global symmetry. For NF is equal to NC plus 1, it turns out once again you have a moduli space of vacua. In this case, it turns out the singularity of the moduli space is not lifted. It continues to be a classical singularity where the gluons would have gone massless. It's not lifted, but it turns out that you can show, at least plausibly argue, that that's not because gauge bosons become massless, but it's because some new dynamical degrees of freedom become massless. So no superpotential. Sorry, this is NF, yes, NF is NC plus 1. So no superpotential. That's why you can have this moduli space. The moduli space has a singularity which is not lifted, but not interpreted as a sign of no confinement. There's confinement, but new degrees of freedom. So baryonic degrees of freedom become independent of the mesons. But that singular point continues to exist. At that singular point, all symmetries are restored. So in this case, you have confinement without chiral symmetry breaking. Then, when NF lies between 3nc by 2 and 3nc, I'm leaving this window for last. When this happens, okay, the theory in the IR goes to an interacting conformal field theory, a fixed point of the renormalization group. Actually, that this happens near 3nc was obvious from perturbative calculations, from what's called the Banks-Zaks fixed point, supersymmetric Banks-Zaks fixed point. But this window extends all the way to 3nc by 2. Okay? And in this regime, where NF goes from nc plus 2 up to, but is less than 3nc by 2, the theory becomes free in the IR. Continues to have massless gluons, but not interacting gluons. Actually, these are called magnetic gluons. Not interacting gluons, but free gluons. Becomes a free theory in the IR. Okay? And the last thing that Seiberg also demonstrated was that in this regime, in this range, where interesting things are happening, there is a dual description of IR behavior. In terms of a second gauge group, which is also an SUN gauge theory with quarks, but with NC prime equals NF minus NC. There's a second description of the same IR behavior. The description is in terms of the IR behavior of another gauge theory. Another gauge theory with gauge group, NC prime equals NF minus NC. And it's the same as the previous theory, except that there's one more complication. This theory has, in addition to the quarks, it has a singlet field, which I'll call Mij, a new chiral multiplet, which transforms under SUNF times SUNF global symmetry. And there's a superpotential, which is Q tilde J. I should call this. These are the quarks of the dual theory. Okay. And then Seiberg argued that under this theory has similar behavior in this range, but where this strongly interacting quantum field, conformal field, fixed point, where the conformal fixed point is strongly interacting in the original description, namely near NF equals 3nc by 2, it becomes weakly interacting in the magnetic description. Namely, it becomes NF prime is near NC prime. Near 3nc prime. Moreover, this region, where the theory is free for the original description, is a phase in which the dual description is not asymptotically free. It's just free in the IR in magnetic variables, and that's what gives you. That's what defines that. That's why you get free description. Okay, I need to stop here. I'm really sorry about this. I'm sorry we didn't have more time to say more about these things, but sorry.
Couple of very quick questions.
Yes.